Okay, so in your lab, you're going to determine the G value. So, but first we need to analyze what is happening in a pendulum. So here's some pendulum physics. You can write this right on your lab. So this will be your analysis now. So this will be the results. So we can put this under results. So you have your experiment. Okay, remember the 6 steps in the scientific process. You have your purpose, hypothesis, experiment. Number 4 is the results, and then conclusion and application. So under your results, we can write this down. So your pendulum is just hanging down, so it's called a static equilibrium right now. So I'm going to give it some amplitude. Okay, don't worry about the vocabulary. I'm going to just swing it. So I'm going to just lift it a little bit. Now with a pendulum, you want to give it some angle, but you don't want to give it too much angle. I don't want to actually pull it too much, more than 45 degrees, because you know what happens if it's too high, it could become erratic, like it's going to be swinging crazily. So we don't want to make it too high. So I'm going to give it some angle, which we don't care about, we don't need to know, but here's what we need to know. All right, so when the pendulum goes down, as the pendulum is here between, I'm going to call this V1, V2, and of course it's going to swing to the other side. But you know what's going to happen if you were to swing this and just let it go, will this actually swing back to the original height? Can I get a brave volunteer? Carl, thank you for volunteering. Okay, Carl's going to be the brave one here. So Carl, you're going to be right up against this pole or this smart board. Okay, you're back. Okay, it's there. So, okay, we're going to go right there. Okay, hold on to this, Carl. Okay, you see that hook is actually touching his forehead, and I'm going to make sure he doesn't back up. Okay, and you're just gonna let go, Carl, let go. Can't move. Okay, there you go. Almost touched him, but just a little bit, right? And he didn't move. Couldn't, because I was holding the smart board steady. So guess what happened on the other side? So when this went up, and let's call this one V2, V3 actually, V3, because this is now V2. What happened? How come it didn't quite reach the original height? It didn't hit him on the forehead. Remember, the pendulum was touching his forehead. When he let go and it went back to him, it doesn't quite go back to the original height. It becomes less and less. Why? It lost energy to where? Where did it go? Where did that energy go? That's called gravity, right? The energy came from gravity, gravitational energy. Where did it go? What's around us? Air, the air resistance, right? There's always going to be air resistance, and also because of gravity, where does gravity want to take that pendulum? Would it be in what we label 1, 2, or 3? 2 would be the final destination, right? Right now, that's where gravity wants it. It wants it right there. That's the static equilibrium. That's the final destination. The gravity wants pendulum right here, right? So where do you think would be the maximum speed of that pendulum as it's swinging? Would it be 1, 2, or 3? So here's 1. I'm gonna go, where's 1? 1 is on this side, so 1 is on this side, so there's 1. What's the velocity right now? What's the speed right now?
0.
0. So V2 will be here, and then V3 will be there. So let's take a look at the V1. So V1 is 0, okay? What happens to this pendulum as it swings to position V2? What is happening to its speed? It's increasing. Why is it speeding up? Well, why did it go there in the first place? Okay, if I'm in outer space and I just let go, if I remove my hand, what would happen to this pendulum in outer space? It will stay here, just like that, right? And then when I let go here on Earth, it wants to go here. But why did it go on the other side? Yeah, momentum. What's the other word that we just learned in Newton's laws? Law number 1, inertia. Okay, so it's gaining speed because gravity is taking it down, and because of its inertia, it's going to go down the other side. That's just the inertia. But yes, it wants to take it to the position 2. Okay, so where is the maximum speed? Right here, isn't it? So that's where the maximum speed is of the pendulum. Why? Because right here, it's going to accelerate with some positive acceleration. I can't call it G though. Why can't I call it G? This one right here. Is the acceleration exactly 9.8? Why not? Yeah, there's some horizontal force there as well, right? It's not a free fall. That's 9.8. Okay? So when it goes down, it's going to, what's happening to the speed on the way up? Here, what would be the speed at the very top on the other side? Zero again. It stops, right? So what's happening here? It actually is slowing down, isn't it? And then it does it over again. And then it repeats itself. On the way down, it's a positive acceleration, maximizes the speed, negative acceleration until, you see the pendulum? Back to where it should be. Right in the middle, right here, static equilibrium. So that's what's happening with the physics behind the pendulum. In your experiment today, what we're gonna do is, if you take a look at, let's just do some observation here with a pendulum. Okay, so I have a pendulum right here. Okay, so what do you think? I want you to make a prediction. If the length of the string, this length of this rope, okay, is this long, and it's swinging this fast, okay? Just observation, no timing, we're not timing yet. What do you think would happen if I cut it into half the length and I give it the same amplitude? Look what happens. Not doing anything, I'm just, see what I did?
It loses its speed faster?
That compared to, you could see it, right? You can see how much slower it is when the rope is long compared to when it's shorter, right? How come?
Does it lose speed to the rope?
Less travel time.
So the distance would be, I'm doing, okay, I'll go this way, about arm's length. Okay, so if I release it, it's going this way. If I cut it in half, I'm still gonna go this way. What would be less? What changed?
Further distance.
The distance traveled by which? By the actual pendulum?
Yeah.
Okay, so it changed, the distance traveled would be the swinging this way, right? So when you change the length, something else changed. Okay, let's analyze this here. This is the relationship that we found out. The T is proportional to L, right? What does that mean? The longer the string, this by the way is the L. The L is the length of the actual rope. So the longer the rope, the blank, the swinging. What is it? What, was it faster or faster or slower? The longer the rope, the slower the swinging. So when you say slower, what does that do to the T? Slower means more time, right? So more L, that means more T. So that's what we found out. Okay, so here's the relationship. This is by experimentation. This was not done by derivation. So scientists did this many times, and they found out that the period of a pendulum is actually equal to, leave some room right here, L over G, and it was actually a square root. So we know that it's direct proportion, but it's not just T over L, it actually is T over root of L. And right here, the constant that makes this equal is 2 pi. Why 2 pi? Yeah, okay, so even though the pendulum is not really traveling in a circle, look at this. The fact that it curves, it is actually a part of a circle. It's just a slice of a pie. Okay? So whenever you take a slice of a pie, you're dealing with 2 pie. Even though you're only taking a tiny sliver of that apple pie, you're dealing with 2 pie. Okay? So 2 pi means there's some curving happening here, and whenever there's a curve, it is a part of a circle. So this is the equation that we're going to be using to calculate the G in our mini lab. So you're gonna have to isolate the G, okay, on your own, and we're gonna do this as a group because we're only gonna have one pendulum here, and you guys will just get the data that we have and put it into this formula. So you're gonna have to isolate the G on your own right here. Okay, so that will be the results. All right, ready? Are you guys ready with your stopwatches? Okay, so we'll take our average. So the more people timing, the more accurate we will have, right? So you guys, you're on this mode now, stopwatch mode. Okay, so what I'm gonna do is I'm just gonna give it like this. Okay, that's about 40 degrees, okay? So this is what it's gonna sound like. 3, 2, 1, go. So when you hear the word 1, it's ready to say go. That means you have to press start when you hear me say go, okay? Again, not yet, it will be 3, 2, 1, go. So when you hear 1, it's ready to go. All right, 3, 2, 1, go. 1, 2, I'm gonna do 10 cycles. 3, 4, 5, 6, 7, 8, 9. Get ready, stop. Okay, so I'm gonna collect your numbers, and even if your numbers were, this is what I got. Okay, so let's take a look at your time. Now this is called time because it's not called period yet. So this is little t. Okay, let me distinguish that in a second. Let me just collect your numbers before we lose that. So I've got 21.05. Okay, who wants to give me theirs? 21.24. Anyone else? Just who? We'll go in order. 20. Ranyo? 0.49. Okay, Sue? 21.53. 0.42.
39.34.
Okay, Nick?
21.2.
23. Jess?
21.78.
Okay. Fatuma? Ibrahim? D? 20 point? Oh, okay. And Brenda, you did one? Oh, that's okay. You know what's really cool? Look at that. Look at the swinging of the pendulum, how it went that way. Remember I lifted it this way? I went this way, right? And now it actually starts going this way. Why? Let me tell you something really weird here. The rope actually is still swinging in a straight line. Something else moved. At about 800 miles an hour. The earth. The floor moved. Our frame of reference has moved. So this thing is still moving, except our earth has turned. Okay? That is mind-blowing. It's called Coriolis effect, and that affects hurricanes, tornadoes, the toilet when you flush it. Okay? Sink when you put cream in your coffee, it starts to swirl like that because the earth is turning. Anyways, Coriolis effect. Yeah, fascinating. Okay, can I get okay, since I have it here, I guess I'll do the average for you guys. While I'm doing this, you guys go ahead and isolate your G so you're ready for your equation. Go ahead and do your equation isolation. ready to get back together here. Okay, so this is our average time for the 10th cycle is 21.348 seconds. I'm not going to round off right now because we want as accurate as we can. Now this is the 10 cycles though, right? 10 cycles. So how do I know how to calculate for 1? So this is basically the definition of the big T. The big T that we have in our equation is called period. And period is basically the time it takes for 1 cycle. That's it. So you just take this and you divide it by 10, right? So you take your time, 21.348 divided by the 10 cycles, and you're gonna get 2.1348 seconds. Let's keep all those digits. So that is our T. Okay, so knowing that, we have 2 pi, and use the function the pi on your calculator. Don't just press 3.14. Okay, actually find the symbol pi, because pi, by the way, you all know, is like the Mobius strip. It's infinity. It's the number of infinity. It never ends. Why does pi never end, that value? And we're actually building quantum computers so that we can get as many digits as possible. And that gets us to a lot of the quantum stuff we're doing. Why does pi not end? What shape are we talking about when we talk about pi? It's a circle, the circle end. Circle has no end, right? Circle end, it just keeps going round and round and round. So pi, use the pi in your calculator. Okay, what's the formula for your G? I'm going to leave that up to you because you are going to hand this in, right? You're going to hand this in. A good copy of this is going to be worth 10 marks. So I'm going to get you to isolate your G, okay? Plug in the T right here. The big T is 2.1348. That's going to go for that. And you've got your pi. You've got the L. What is the L? We haven't gotten the L yet. So I need to measure the length of that pendulum. So you're going to calculate your G. So you measure from there. Can you guys spot, am I right at the end of the rope? Brenda, do I see? Is my meter stick right at the end? Is that good? Okay. This is 1 meter and I have to measure to the center of the pendulum, 13. So 1.13 meter. 1.13 meter length. There you go. We have everything that we need, and we just need to calculate the G. Okay, hint. See this G right here is inside the square root. How do we get rid of that square root? Okay, so when you have something like you have the number 2 and it is a square root. This actually means 2 to the power of 1/2. That's what a square root means, is to the exponent of 1/2. So look at this. If you actually square it, if you square this, you square that, see this? You're canceling it. That's what that is. When you square a square root, this is what you do. It's 2 to the power of 1/2. That's the square root part. Okay, so when you make it to the exponent of 2, look what happens. The number 2 cancels, and it's just number 2. So if you square this, right, which means you got to square that too, what happens to this? L over G. It just becomes L over G. Did we know this part? So this becomes T squared. What happens to the square of 2 pi? 4 pi squared. This just becomes L over G. There you go. You have released that square root. And then just isolate the G from there, okay? I want you guys to make this. It's 10 marks, almost. Curious what our G value is gonna be. Okay, so write a small conclusion and an application. Why is this method actually more? Do you find this easier to do than the dropping of the balls that we did before to calculate the G? To determine the G? Like I said, I did this on a plane and I was able to calculate the G that way. It's a useful method. Okay, so write up a conclusion, summarize what you learned, right? And then your application would be, how is this useful? This is something that's being used in any technology device right now. All right. Okay, I'm gonna give you 5 minutes to wrap it up and hand it in, okay?